Section 2.1, Writing and Graphing Inequalities. What we're going to be looking at today is moving beyond equations into inequalities. Inequalities are statements that compare two values, and rather than saying that they're equal, it tells us one of four other things. We have four different symbols we can choose for inequalities. We have the less than symbol, the greater than symbol, the less than or equal to symbol, or the greater than or equal to symbol. And so each of these symbols mean different things, and a lot of times there's some key phrases here. In real life conversation, we may say it another way as opposed to less than, greater than, etc. So for less than, we might say it's something is fewer than, and instead of greater than, we'd say is more than. Is less than or equal to could also be said as is at most, or is no more than. And greater than or equal to, we could say is at least, or is no less than. And so there's different ways to phrase, and there's other ways beyond these here. These are just the most common. And so what we are looking at here is we have three examples. I actually have an equation and then two different inequalities. The first equation, x plus 2 equals 3. First inequality, x plus 2 is greater than 3. And the second inequality, x plus 2 is less than or equal to 3. Each of these equations or inequalities tells us that something has to be true about x in order for x to be a solution. In order for this first statement to be true, I have only one option for x. The only thing that's going to make x plus 2 equal 3 is if x equals 1. 1 plus 2 equals 3. There's no other way that I can add something to 2 and get 3. That's my only option. So there I have only one answer. For the other two, though, there are inequalities. I actually have more options than that. When I say that x plus 2 is greater than 3, I can pick anything that's bigger, that's going to make that left side bigger than 3. It doesn't matter how much bigger. If I pick 5 plus 2 is 7, and that's greater than 3. If I pick 18 plus 2 is 20, and that's greater than 3. So what I can actually pick is I can pick anything that's bigger than 1, because adding 1 to 2 just makes it exactly 3. So if I add anything that's bigger than 1, greater than 1, I would end up having a solution. Anything bigger than 1 will make my original inequality true. 1, however, does not make it true. 1 plus 2 is 3, which is not greater than 3, so it doesn't work. Now in my third example, x plus 2 is less than or equal to 3, I have to think about adding something to 2 that's going to keep it less than or equal to 3. Well, 1 is a viable option here because 1 plus 2 equals 3, and so that satisfies the or equal to requirement. I could also pick something like 0. Maybe 2 is less than or equal to 3, and 2 is less than 3. I could pick a negative number. The only thing I can't pick is anything bigger than 1. So what I could actually choose is anything that's less than 1 or equal to 1. I actually can choose that. So for my first equation, I had only one solution, x equals 1. But for my two inequalities, I actually have an infinite number of possibilities, which doesn't mean all real numbers, but I do have a lot of options. With my first inequality, I can pick anything that's bigger than 1. With the second inequality, anything that's less than or equal to 1. And those are my options. So, hopefully this gives you a quick introduction to what inequalities are and what they look like. Now let's work with them. One thing that is often tricky is translating from a verbal to an algebraic representation of an inequality. So I'm just going to try some practice with that here. We could say a number x is at most 4. So I think about the two things I'm comparing. I'm comparing a number x and I'm comparing the number 4. If I remember from the last page, the last slide, that when I say at most, that means generally less than or equal to. That means that at most, x can be 4. It's allowed to be less than 4. So it's less than or equal to 4 is the translation of that. Next example, double the number y is at least 8. Well, double the number y is going to give me 2y. And at least tells me it's going to be greater than or equal to 8. Because at least means that the smallest possible thing it's going to be is 8. It might be bigger than that, and so that's why we use the greater than or equal to. And then finally, 4 less than a number z is no greater than 10. So 4 less than a number z, that's telling me I start with z and I'm taking away 4. And I'm going to compare that to 10. Now if I say it's no greater, I'm not allowed to be bigger, I'd only be allowed to be less than or equal to. And that's what we have. Now what we could do is we could actually solve these two inequalities a little bit further. We're not going to worry about that for now, but it wouldn't be too tricky to get our answers just in terms of x, y, and z. So that's how you translate. You write the inequality based on the written description. Now when you have an inequality, it's pretty easy to check if a particular value is a solution, but it's almost always impossible to list all of your solutions. So we can actually figure them out separately, but it's hard to list or figure out individual ones, but it's hard to list them all. Sometimes impossible. So with 2x minus 8 is less than 7, I just want to know, are 5, 7.5, and 10, are they solutions? So I'm going to start by plugging in. I'm just going to write this out. I'm going to have 2, and then let me get a nice bold color here. I'm going to plug in 5 for my x and say minus 8 is less than 7. That's what I want to know. Well, based on order of operations, 2 times 5 is 10, minus 8 is 2. And is 2 less than 7? It certainly is. So 5 is a solution. What about 7.5? I'm going to plug in here. 2 times 7.5 minus 8. I'm hoping that that's less than 7. Well, 2 times 7.5 is 15, and 15 minus 8 is 7. Is 7 less than 7? It is not. It's equal to 7. It's not less than 7. So 7.5 is not a solution. Finally, we'll just check 10. I think you probably have a hunch where this is going. 2 times 10 minus 8. Is that less than 7? 20. It comes from 2 times 10. Minus 8 gives me 12. And is 12 less than 7? No, it is not. So 10 is not a solution either. And so what we have here is we have one of our solutions, but we actually have an infinite number of them. We just haven't listed them all. We can't list them all because there's infinitely many of them. So we want to figure out a way that we could actually figure out what are all of the solutions. And the way we would do that is by solving the inequality. We treat it like an equation in order to solve it. Let's take a look at exactly how we would solve that inequality and then how we can use a graph to represent the solution set. First thing that we're going to do is we're going to look at this inequality, 2x minus 8 is less than 7, and try to solve it like it was an equation. So to do that, I want to get the x by itself. I'll start by adding 8 to each side. That brings me to 2x is less than 15. That's 2x, so I'm going to divide to get rid of that 2. And it leaves me with x is less than 15 over 2, or, if I wanted to write it a certain way, 7.5. Ah, that explains why 7.5 was not a solution on the previous page, because x has to be less than 7.5 to be a solution. 5 is less than 7.5, that's why it worked. 10 is not less than 7.5, so it didn't work. You can see now that you have lots of options. Anything less than 7.5. 7.4, 7, 6, 0, negative 5, negative 600. Any of those will make the inequality true. So this is considered our solution set. X is less than 7.5. All those numbers. Now it's hard to write out those numbers. It's impossible to write out those numbers. But we can use a graph on a number line to show it. what we do is we actually are going to just find 7.5 on the number line. So if you happen to have some other points, you've got 5, 6, 7, 8, 9, etc. You just have to locate where 7.5 is, which is in between the two. And we're going to put a particular type of circle at 7.5. Now, because it's a less than and not a less than or equal to, we're going to put an open circle. Because what we're saying is, I don't want to include 7.5 as an answer, but I want to get really close to it. And I can't just say 7.4 or 7 or anything like that, because decimals are kind of weird and there's no way I can get there. But now I want to say I want to cover everything that's less than 7.5. And everything that's less is going to be over here to the left of that circle. So I'm going to continue on forever. That right there indicates all of the solutions. Everything underneath this arrow is a solution. 7, 6, 5, 5.5, 4.9999, pi, 0, negative numbers. All of these. Not 7.5 because the circle's open. Nothing bigger because there's no arrow. I've drawn this above the number line. You can see in the diagram here, you should take a look to see the descriptions of all of those. They draw them right on the number line and darken it. That's acceptable. You'll also see some people put the circles open or closed right on the number line, come up and then take a turn, either left or right. Any of those are fine as long as it's clear. You can see, however, that when you have a variable less than something, the arrow comes off to the left. A variable greater than something, the arrow goes off to the right. If it's just less than or greater than, it's an open circle because I'm not including 2. And if I have that or equal to, fill in the circles because 2 would be an acceptable answer there. Alright, so there you go. Hope that makes a little bit of sense. Alright, what I want you to do now is I want you to try to fill in this table, and I'll go one row at a time. But I want you to try to fill in this table here to show the different ways to represent the same inequality. Starting with this inequality here, can we write it out verbally and graphically? Pause the video, give it a shot, and then check your work. Alright, here we go. Alright, so we would read that as x is less than 6, and the graph would be an open circle at 6, and the arrow would go over to the left. Alright, next one. In this row, here's your graphical representation, and fill in the verbal and the algebraic. Alright, let's see how you did. So, we would look at this here and identify that we're talking about everything greater than 4 or equal to, so that's why we say x is greater than or equal to 4. You could also say x is at least or no less than 4, and also would have been acceptable. And this is how you would show it algebraically. X is greater than or equal to 4. The closed-in circle tells us to include the or equal to. Arrow going to the right says we have a greater than. Alright, another example. A number x is no more than 3. Fill in the algebraic and the graphical representation. And how'd you do? Alright, so if a number x is no more than 3, that means it's less than or equal to 3. And graphically, we'd fill in the circle at 3 and draw the arrow off to the left. And finally, last one here. Here's the graph. Fill in the rest. Think. Don't just assume that you know what to do. So, with this, we end up getting x is less than 11. I was hoping that I would trick some people into thinking, oh, we didn't cover greater than yet. It must be greater than. But no, we just don't have greater than on here. If it was going to be greater than, this arrow would have had to come out to the right. But as it is, it's another less than, just like our first one. And strictly less than because the circle was open. We're not including 11. We're saying x is less than 11. And we show it algebraically here. Alright, so that's an introduction to inequalities. I hope that this makes a lot of sense and now you feel more comfortable going forward.